Hello and welcome. This is going to be our lecture video for the periodic trends worksheet. Let's go ahead and get started. Number 1A, each element has three numbers listed under it. Which value represents the atomic radius? It is going to be the first number. What are the units for the atomic radius? Units are picometers. PM, which stands for picometers, which go ahead and write down that that's 10 to the negative 12th meters, meaning that 10 to the 12th picometers could fit in 1 meter. This is our next smallest metric prefix that we haven't talked about yet. It goes milli, then micro, then nano, and then pico. All right, part C asks us to convey our understanding of atomic radius. Go ahead and put this in a complete sentence. But it is basically the size or volume of an atom. Radius is just one way that we can measure size, and everything else is connected to that. So in general, what is the trend of the atomic radius as you go down a group in Model 1? So, and then it says use example from three groups. I'll let you come up with your examples. But as you go down, the radius increases. So, using your knowledge of Coulombic attraction and the structure of an atom, explain this trend in atomic radius that you identified in question 2. Hint, you should discuss either a change in distance between the nucleus and the outer shell of the electrons or change the number of protons in the nucleus. So, of the two, it's the distance between the nucleus and the outer shell that is at play when the radius increases as we go down a group. Here's what we should say for this. As we move down a group, we are adding energy levels. So the periodic table is only 7 periods tall, and that's because the maximum number of energy levels is 7. So each row corresponds to one energy level being filled. So it makes sense to me that if I have to go from one energy level to 2 energy levels, my atom just got bigger. If I'm measuring the whole volume of the atom, electrons included. Maybe we should go add that to part C up here, electrons included. And then every element in period 3 is got electrons all the way out to its 3rd energy level, then 4 energy levels, and then 5, and then 6, and then 7. All right, so it makes sense that as we move down in the periodic table, atoms are getting bigger. But question 4 asks us, in general, what is the trend in atomic radius as you go across a period, left to right? In this case, the radius decreases. You can come up with some examples, but let's just answer this next part. Using your knowledge of Coulombic attraction, the structure of an atom, explain the trend in atomic radius in question 4. So what's happening here is that as we are adding in more electrons, we're also adding in more protons. Those electrons are only being added to the highest energy level, and the protons are able to pull on that energy level with a stronger magnetic force. So it's really all about the number of protons. Allows the nucleus to pull its outer energy level further in. All right, the second page doesn't ask us to necessarily do anything, but I think we can label a few things. We already discussed how the first number here is the atomic radius. And its units was picometers. Radius, I know it's bad handwriting. The second number is ionization energy. And the unit there was kilojoules per mole. We'll talk more about what both of those things mean. And then the last number is electronegativity. And this doesn't really have units. They're just arbitrary units that help us compare one atom to another. All right, let's move on to question 6. So we already did this first part. We located the numbers that represented the ionization energy. This tells us that ionization energy is the amount of energy needed to remove an electron from an atom. Using our knowledge of Coulombic attraction, explain why ionization, removing an electron from an atom, takes energy. So we've got a positively charged nucleus because of all the protons in there, and we have a negatively charged electron. So there's a force of attraction here. The positive charge is pulling on the negative charge is pulling on the positive charge. If we are going to remove an electron, we have to further separate these charges. We have to work against the direction they're trying to pull each other. So it takes energy to pull away. Just picture yourself trying to separate two magnets. You have to put some effort in to pull two magnets apart. This is exactly what's happening, but it's not the same amount of effort for every single electron. Some electrons are held on to very tightly and some are held on very loosely, but all do take some energy to pull away. So which takes more energy, removing an electron from an atom where the nucleus has a tight hold on its electrons or a weak hold on its electrons? I think it's pretty obvious that a weak hold, we can steal it much easier. All right. In general, what is the trend for ionization energy as you go down a group? So as we go down, ionization energy is going to decrease. And we're talking about just removing the furthest out electron. Well, as we go down in the table, that furthest down electron is even further away. So I think that's what we can put in for number 8 here. So the valence electrons are further away. All right, and then number 9, in general, what is the trend in ionization energy as you go across a period? So now remember from atomic radius that moving across a period means that the nucleus is holding on tighter and tighter to that outer shell. Therefore, it makes sense that this would increase the ionization energy. So now using our knowledge of Coulombic attraction, can we explain that? So all we need to say is that the nucleus is holding on to the valence electrons stronger and stronger as we move across a group. VE will be our abbreviation for valence electrons. Now question 11. asks us to make a prediction about metals, but it tells us that atoms with loosely held electrons are usually metals. So if they're loosely held, that's going to be low ionization. All right, it won't take much energy to remove those electrons if they are loosely held. On to electronegativity. So we're getting very close to starting to talk about bonding. So this definition here describes electronegativity as the desire for an atom to attract the electrons when it's in a covalent bond. So all you need to know about bonding right now is that if two atoms are bonded, they share electrons. Well, just because they're sharing them doesn't mean they're sharing them equally. It's possible that one of the atoms is kind of hogging the electrons. So question 12 says, which is the best picture of this? It is B. B shows that we have one of our two atoms in a bond here is attracting their pair of electrons more than the other. And so the one on the left here is going to be more electronegative. Although they're sharing the electrons, this one is being a little bit more greedy on the left. So it was the third number in Model 1. What's the trends in electronegativity as you go down a group? So as we go down, it's going to decrease. For kind of a different reason than the reason that ionization energy decreased. Here, we really care about, can the nucleus attract new electrons? And as we get larger and larger atoms, that the positive charge from that nucleus is just shielded and can't go out and attract new electrons. So that's why we see it decreasing. So explain the existence of this trend described in part A's in terms of atomic structure and Coulombic attraction. As the radius increases, the nucleus cannot attract more electrons just due to distance. So what is the trend in electronegativity going across a period in Model 1? So as we go across, the electronegativity is going to increase. Explain this increase. So as we go to the right, we have a stronger nucleus. And we're not gaining energy levels. And when we do any sort of bonding, that bonding happens in the highest energy level of the atom. All right. The two diagrams below can summarize each of the three trends discussed in the activity. Write atomic radius, ionization energy, or electronegativity under the appropriate diagram. So this one on the right is going to be atomic radius. And the one on the left is electronegativity / ionization energy. The one difference in electronegativity and ionization energy is that noble gases have basically zero electronegativity. They do not want to attract more electrons. So they have basically zero electronegativity, but they have very high ionization energy. They don't want to lose the electrons they have. So that's kind of the only difference. Otherwise, the trend is the exact same for electronegativity and ionization energy. All right, now on to our essential questions. So during this activity, you may have noticed that not all of the data provided in the model followed the trends. Identify 2 places in the model where the property listed did not fit the trend identified in this activity. So one possible spot you might have noticed was oxygen. Oxygen actually broke 2 of the trends. So oxygen with its atomic radius and with its ionization energy, both of them just slightly broke the trend. We don't need to really get into why oxygen behaved a little bit differently there. It's just an example of how this isn't perfect. So, we can't rely on it 100%. When we really need to compare 2 atoms, we should go and look them up, but we can use these trends to make sort of general comparisons. So why is it still beneficial for chemists to understand as many periodic trends as they can? It's just so they don't have to look it up each time. So they don't have to look it up. And can compare atoms. We don't need to memorize the actual numbers. We just need to know which atom is either larger or more electronegative or has higher ionization energy relative to another. Propose an explanation for one of the exceptions you identified in part A. So really it's all about stability. So we can just leave it at that. I will share with you now that electrons really like to pair up. And so that's one reason why an odd number of electrons might be less stable and therefore have something like lower ionization energy or a larger radius. But it's all about this idea of stability. All right, so rank the following elements from smallest to largest in terms of electronegativity. So the correct order is barium has lower electronegativity than iron, which has lower electronegativity than bromine, which has the highest electronegativity. And you can go ahead and explain that, but we'll call that good here for our lecture video. Have a good rest of your day.